In the last little bit of Unit 2, we'll talk about balanced binary search trees. And this is really just a teaser of what is possible. And I suppose for many of you, that will be just repetition. No, sorry, I started the wrong one. There we go. I'll have a list of things on the slide in a second. So the way the question is posed as an open answer thing, we'll probably get a cloud of words without much of a sense of what percentage of people have seen it before. But it's roughly a quarter in the class who have not done an undergraduate degree in computer science. And those are unlikely to have seen balanced binary search trees, whereas everyone who has a computer science undergrad degree is very likely to have seen one variety of those. So I can pretty much predict it will be between 2/3 and 3/4 who have seen it. We will continue tomorrow. Is that actually meaning we should stop now? Of course not. I'll keep the collection open. We can have a peek at it. Here's my list. It's probably not complete. Let me jump to this. So AVL trees and red-black trees are by far the most widely used and widely known ones. There's a few others, and then there's a few more. But let me take a step back and what are we talking about here, if you haven't seen this before. So all of today, I talked about, binary search trees are so cool because the operations are fast. But the operations are only fast if the tree is not too tall. And then I promised you if the keys come in random order in the insertions, everything will be fine, fingers crossed. But if they don't come in random order, it might be linear time. So the worst case for a binary search tree, if the insertion order is not controlled for in any way, is pretty poor. Instead, we'd like to have log n time regardless of the insertion order, in the worst case. And that is possible by various schemes of keeping the tree balanced, where balanced is essentially defined as anything that has height at most log n in all the subtrees. So the typical way to do this is to impose an invariant on the shapes that are allowed. We've seen an invariant on shapes in the heaps chapter. There, the invariant was very simple. Every binary heap shall have exactly this shape if it has n nodes. We'll have to be a bit more lenient with binary search trees. That will not be able to maintain such a strict invariant. But essentially, AVL trees and red-black trees and weight-balanced trees, these are all types of invariants on the shape of the tree that you can maintain. So you have certain rules or certain extra steps for the updates, insertions, and deletions that re-establish that invariant. Just to make it concrete, for AVL trees, the invariant that we have is as follows. If you have any node, then it has potentially 2 subtrees. And then the height of the 2 subtrees, say if this is the left height and this is the right height, then they may differ by at most 1. That's the condition for AVL trees, and this shall be true at every node. So for every node, the difference in subtree heights is at most 1. It might be a bit, it might need some thinking how to maintain this, and this is another 2 hours or so of lectures to do it, so I'll not do it. But you can watch the videos, which don't touch AVL trees. They touch red-black trees. That's a slightly different variant. I'm not going to define it formally. It's a similar idea. You keep some certain invariants. And it's a little faster to implement. That's why people prefer it. The Java library has red-black trees. Same for the C++, STL, Python famously doesn't have binary search trees built in. Big shame, but there's extra libraries. There's a few others. There's another option. Instead of having these invariants on the shape that somehow need to be maintained, there's other options that also can work. I just want to throw these out because they're ideas that are interesting beyond just binary search trees. One is amortization. We talked about this before for the doubling arrays. Amortization is the idea that some operations might be expensive, but if you have a long sequence of operations, on average, each operation is cheap. Splay trees are the prime example where a somewhat magic rule how to change your tree guarantees that if you have a long sequence of updates, they will always come out cheap. There's actually a deep open question, open for 40 years in computer science, that people are still struggling with, whether splay trees are the best way to do this kind of update. I can tell you a bit more about this offline if you're interested. It's very fun and a really cool research topic, but it's beyond the scope here. I just think it's useful to know that these exist. They have some properties that are useful in that they don't need an extra field. For AVL trees, you essentially have to store the height of these subtrees, and splay trees avoid that. The second option is randomization. What I said previously, the height is usually good if the insertion order is random. You can do better than that. You can enforce the randomness. So even if someone inserts things in a bad order, it's still unlikely that you see a tall tree. But you kind of enforce the randomness by explicitly doing random things. It's very different and much more powerful. Again, some of these are useful in specific scenarios, like skip lists are good for concurrent data structures and so on, but all a bit beyond the scope here. Just want to throw out a few things that if you feel that unit was a bit underwhelming because you've seen all that before, there's a lot of cool stuff that ties into this and that's worth looking at. I have one big slide to summarize what we've done in this module, in this unit. We've talked about priority queues on that side, the binary heaps, and we've talked about symbol tables or ordered symbol tables and binary search trees. And here are all the running times that we achieve. So here, assuming a balanced binary search tree, any of the ones from the previous slide would do. And if you look at this, you might wonder why people are at all excited about heaps. Because essentially, all the operations that a heap can do, like insert and removing the maximum, a binary search tree can do that too in the same time. So how would you do delete max in a binary search tree? You could do min and max in logarithmic time, and then you can do a delete afterwards, logarithmic time. So factor 2 slower, fine, but apart from that, if you just look at the big O statements, it's the same. There's one exception, and that's the first line, the construction. If you want to build a heap from a set of elements which are not in sorted order, you can still do it in linear time. We discussed this with the build little heaplets and do the sync. For a binary search tree, you cannot do that. And soon we'll prove why. But that seems to be the only thing. So you might come out of this, or some of you may have come out of an undergraduate algorithms class feeling a bit cheated. Why do people care about this priority queue abstraction if the best we can do, binary heaps, are not really faster than the general purpose binary search trees that can do that at the same time, plus a lot of other operations? And my counterpoint to that would be the abstraction of a priority queue is still useful. One, it can express that you only need certain subsets of the functionality, but two, there are better implementations. So the reason you don't hear about those in most algorithms classes is that they're incredibly complicated. And so for the state of the art in research, I know that there's an educational implementation, but not one that beats binary heaps on small inputs. But at least in theory, it's possible to support the priority queue operations much faster, so that only delete max is logarithmic, whereas insert and change key is constant time, and that's even in the worst case. And for various reasons that we'll talk about in the sorting chapter, that's completely impossible for binary search trees. So there's a clear separation between those two abstract data types. And so it can be useful to keep those around, even if the best implementation you currently have doesn't seem to get you any edge.